Hi there. Hopefully if you're watching this, it helps clarify any questions you might have. So the last big example we're going to do to wrap up kind of the energy topics for this chapter and for this year is trying to incorporate everything. So we're going to look at a car engine, which is going to act like a big calorimeter for us. So let's read through this. When octane burns in an engine, heat is released into the air and the engine. However, some of the heat is absorbed by the cooling system, ethylene glycol. What mass of octane burns to cause 20 kilograms to heat from 10 to 70 degrees Celsius, given the specific heat capacity? And the molar mass is that, we'll just add in of octane here. Okay, so what's interesting right off the bat is that we have a temperature change here. So we're going to be using calorimetry data for this. So let's start off with it. What's the question? What mass of octane burns? So when we analyze this, we'll do a little analysis off to the side here. To answer that question first, right off the bat, the mass is equal to the number of moles times the molar mass. Now, we can find the molar mass, no problem. Okay, we'll call this equation 1. We read it off the periodic table for octane, which is C8H18. But there's no information there that tells us what the moles are. So we need another question or another equation. Now, for the number of moles related to energy, there was an equation with the molar enthalpy and the overall enthalpy change. So if I rearrange that, the number of moles is equal to the enthalpy change divided by the molar enthalpy. Now, obviously, we have neither of these. Okay, so where do we get these ones from? Okay, so the number of moles is what we're trying to find. The enthalpy change, okay, can be determined as the actual enthalpy change. And we'll come up with our equation for that because we have measurable data for it. We have calorimetry data. On the other hand, the molar enthalpy is one that we usually determine theoretically. Okay, and we can use just a balanced chemical equation for that. All right, so let's come up with our equations here. So for the enthalpy change involving a calorimeter, we had said that it's equal to the negative heat of the surroundings, which is equal to negative mc delta T. Okay, now in this case, the surroundings are the ethylene glycol cooling system. Okay, so we'll just kind of highlight that here, right, for ethylene glycol, because we said it was important to keep organized the variables that are together. For a theoretical enthalpy system, our molar enthalpy, we said it was the enthalpy change divided by the number of moles, where this came from standard enthalpies. So we'll just kind of write that in brackets here. And the number of moles comes from the coefficients. So following this roadmap here, okay, and then just solving it in reverse, gives us all of the information we need to find the mass. Okay, and rather than trying to memorize questions, it's important to understand the link between the variables. And we start from here. So we'll say we'll solve from the bottom up. So if we start with equation 4, because we can have the information for that, we'll be able to solve this question. All right. So the first thing we need, because we're using formation enthalpies, is a balanced equation. So because we're working with combustion, okay, and octane is a liquid, plus oxygen produces carbon dioxide and water, and these are all in the gas form. Okay, so when we balance this, we start with the carbons, 8 and 8, move to the hydrogens, 9 gives us 18, and then overall we've got 25 oxygens, so we're going to put here, we'll just clean this up a little bit, 12.5 times 2, and it's okay to use decimals or fractions. So there's our balanced chemical reaction. And now we're just going to solve our equation. So number 4 is what we'll start with. Okay, the enthalpy change is we're going to use the standard enthalpies of formation for that. So the sum of the enthalpies of the products minus the sum of the enthalpies of the reactants. So it gets a little messy here, but we'll do our best. So we've got 8. I'll just kind of condense it here. And don't forget, these values come from the table on page 320 or your reference sheet. 9 H2Os. Remember, we're working with the gas here, so we choose the appropriate value. Okay, only 2 products. Subtract the value for 1 mole of octane, and its value from that table is 250 kilojoules per mole, and then 0. Again, because it's pure oxygen, it has no contribution to it. So when we simplify that, we get an energy change of negative 5,074.1 kilojoules. And again, take your time to solve that. And that is for 1 mole of octane. Now don't forget why we're using octane, because in the end, that's what we're being asked about. Okay, so if we're being asked to find the moles of it, we need to find the enthalpy associated with octane. So now based on that, we can say delta HR is equal to, now it's easy to divide by 1, joules per mole of octane. So that is our blue variable. Okay, we found our theoretical value for that. All right, so we're done there. Now for number 3, and I'll just kind of color code that there. Number 3, we're going to go into the green ones. So delta H is equal to negative Q equals negative MC delta T. Just kind of put that up here. All right, now the surroundings are not water here. We're told that they're ethylene glycol, so that means we have to use the mass, heat capacity, and temperature change of ethylene glycol. So 20,000 kilograms is 20,000 grams. Its heat capacity is 3.5 joules per gram degrees Celsius. And its temperature change from 10 to 70, it increased 60 degrees Celsius. So that means that all of this energy, the system, because the surroundings absorbed it and increased their temperature, the system's released it. So we get a value of negative 4.2 times 10 to the power of 6 kilojoules. All right, now I've converted that because it was 4 billion joules, and we can punch that in again to verify. 20,000 times 3.5 times 60. Okay, we'll just fix that up here. That's actually in joules. All right. So if that's the number of joules that are there, okay, and you can always double check. I always check my numbers a few times just to be safe. 20,000 times 3.5 times 60 is 4.2 million joules. All right, or we can say, we've got some room below here, so I'll steal this. Negative 4.2 times 10 to the power of 3 kilojoules. Right? So that's our green variable there. And now we've got everything we need. We know the actual energy released. We know theoretically how much is released per mole. So what we can say for equation 2 now, which is our yellow variable, moles are equal to the energy released divided by the molar enthalpy. So in this case, we've got negative 4.2 times 10 to the power of 3, not negative 3, kilojoules, divided by 5,004 kilojoules per mole. So our kilojoules unit cancels out, and we're left with mole. Right, and we punch that in. The negative signs cancel out, which is good, because we can't have negative moles. E to the power of 3 divided by 5,074.1, 0.83 moles. Okay, so there's our yellow variable there. So if that's all the number of moles that were being used, our last step for this, we can say the mass is equal to the moles times the molar mass, which we were given. So we can say that value there times 114.26, 94.6 grams. Okay, following our units throughout. And that's our final answer. Okay, so we can say, therefore, to solve this question here, when octane burns to raise it 60 degrees, 20 kilograms of ethylene glycol 95 grams, about 95 grams of octane had to burn, right? And its density is not 1-to-1, so we can't say it's 95 milliliters, but it's pretty close to something like that. So that's an integrated example. There's a lot of things that go into that, right? Have a review over it if you need to. But this combines everything that we learned in the unit topic-wise, calorimetry data, taking a look at a car, which is like a giant calorimeter, and then combining enthalpies from Hess's law and formation energies. So there's some homework questions at the bottom, if that helps. If I go back to our PowerPoint to finish up, I recommend always jotting down the formulas and just seeing the difference between the variables. Okay, and then the homework questions apply as is. There's some chapter review questions, and there's lots to practice with. So feel free to reach out if there's something still confusing, and we'll aim to help you the best we can.